Hi everyone, welcome to this second ECON 333 lecture. Today we are going to go over the second and third part of chapter 1. So we are still talking about probabilities, but this time we are going to complicate things a little bit by talking about two random variables instead of one. After that, we will then go over some common distributions that you should know about. You should know how to use them, you should know how to manipulate them, and we will go through a couple of examples so that you can get some experience with it. But first, the usual disclaimer. I do not allow this content to be published without my consent. If I see this content uploaded online, I will take it down and report whoever uploaded it. The outline for today will be to talk about the relationship with two variables. In fact, talking about two variables is the same thing as talking about 3, 4, 5, and so on. 2 will be the easiest case, so we'll just stick to that. First, I will introduce you to the concept of covariance and correlation. This is pretty much a sequel to what we left off last week when we talked about expectation and variance. Covariance and correlation are two other formulas you will have to know and have to manipulate in the midterm, the final, and in some assignments. Then I will talk about what we call conditional probabilities. That is a very important topic in econometrics, in stats applied to economics problems. So I need to give you the foundations of conditional probabilities. Along with conditional probabilities, we'll find conditional moments, conditional expectation, conditional variance, and I will finish that lecture with an exercise that is going to cover pretty much all of the concepts we are going to cover first. I used chapter 2.3 in Stock and Watson to base most of the content in this lecture. So if you want to read extra stuff about it, that's a good place to start. But there are other textbooks, other econometrics textbooks, other probability courses, textbooks, and lecture notes online that you can find. These are pretty common concepts. You can even find them on Wikipedia. So don't hesitate if these lecture notes are not self-explanatory enough. So the reason why we look at two random variables is because most of the time we do not deal with one random variable, we deal with two or more. And very often, especially in economics, variables are correlated, which means that the variation of one is going to influence the variation of the other, or the probability of one happening will affect the probability of another one happening. Kind of the same way we were talking about two correlated events in the previous lecture, here we are going to talk about two different random variables. For instance, the proportion of smokers is not the same among men versus women. So the probability of meeting a smoker is different if you are thinking about meeting a man first or if you are thinking about meeting a woman first. Among women, there are less smokers than among men. I believe this statistics is maintained through many countries. I can think of Canada for sure, France for sure, probably the US as well, and probably other European countries. So the random variable that is equal to the next person I meet is a smoker. The probability of meeting a smoker will be different if I am meeting a man or if I am meeting a woman. And so gender will be correlated with smoking status. Instead of talking about smokers among men versus women, we could think about the proportion of smokers among Canadians versus French people. The proportion of smokers is definitely not the same among Canadian versus French. So, if you are in France, there is a high chance of meeting a smoker in the street than there is in Canada, and by far. I was actually very surprised when I went back home the first day, even after getting off the plane. It was like 8:20 in the morning, and I was going through the airport, and I saw a smoking area outside, and I was super surprised to see that many people smoke at 8:20 in the morning, and I forgot. This is France. Everybody smokes. Whereas in Canada, I see one student or two every now and then, but that's pretty much it. Consumption is not the same between rich and poor households. So consumption is affected by income. Those are two different random variables. Somebody who earns more money will, on average, will tend to consume more than somebody who earns less. Again, two variables which are correlated. And these ones are positively correlated. The richer you are, the more you consume. So, the measures we talked about in the previous lecture, expectation and variance, will not be enough to talk about how two variables are correlated, how they move together simultaneously. And this is why we need measures of covariation between two random variables. And this is what I'm going to get into right now with these two new measures. The covariance between x and y, which is denoted cov, xy, or we also use the Greek letter sigma and we put xy as a subscript, the same way we would use sigma squared x for the variance, is the expectation of the products of the deviations from the mean. Again, super tedious term to talk about. The formula is actually easier to look at. So, first it says expectation. So, first thing you see on the slide will be, and the formula will be expectation. And then of the products, this is why we have bracket times bracket, of the deviations from the mean. So, we have x minus its expectation, and then we have y minus its expectation. Now, to decompose this expectation, we need to look at the joint probabilities. We don't need to look at just the probability of y being equal to something and the probability of x being equal to something separately. We need to look at both being equal to something at the same time. The intersection. And this is why we need to compute a double sum. You don't need to know the formula by heart, but you will need to know how to compute it. And I will show you today an example so that you can get an idea of how the formula should go. So we are going to sum the probabilities times the deviations from the expectation. Now, x can take different values and y can take other different values. And this is why we have two sums. We sum over all the values that y could take. We have the index I that is on the random variable y's realizations. And then we have the index j, which is associated to the random variable x. There is an equivalent formula, which is the one I use most of the time, but both are useful, which is to compute the expectation of x times y minus the expectation of x times the expectation of y. The advantage of this formula is that when you already know expectation of x and expectation of y, then you only need to compute this single thing. And this thing alone is kind of easier to compute, not as complicated as this huge formula. This formula should remind you of something we've talked about already. Deviation from the mean, expectation, this should ring a bell and it should remind you of the variance formula. Except that this time we don't have a square because it's not x minus expectation of x times x minus expectation of x. There is some x on the left and there is some y on the right. I'm not sure what you mean by denoted to equal 1. I don't see anything here in the formula. Do you mean the summation terms? Oh, the summation terms means that those are indices. I starts at 1, so y1 would be the first value that y takes. But y doesn't mean that it's going to be equal to 1. Y could be equal to 3, 4, and 5. And in this case, y1 would be 2, y2 would be, so y1 would be 4, y2 would be 5, and y3 would be 6, for instance. So, remember that big Y refers to the general random variable, the variable that could take a bunch of different values, and the lowercase refers to the actual value it will take. So, small y refers to one of the values that big Y can be equal to. So big Y is a general variable, small y is a particular number it can take. For instance, when you throw a die and you look at the number you obtain, big X is going to be the number you obtain. That's all. You see, I don't give you any number. It could be 1, 2, 3, 4, 5, or 6. If I observe a 2, because I get a 2, then I will say small x is equal to 2. This is a realization of my random variable. This is one value it will take in particular at one point. Okay. The covariance, like the variance, has a couple of handful properties that you should be able to manipulate for the exams, the assignments, and so on. So I will use the example of 3 random variables, x, y, and z, and I'll take 2 constants a and b. The first property is that a negative covariance means that the 2 random variables evolve in opposite directions. It means that on moments where one of them tends to be high, the other one tends to be low. For instance, you could imagine that the amount of calories I eat will be, well, calories is not, the quantity of exercise I do will be negatively correlated or will have negative covariance with my weight. If I do more exercise, I burn more calories, and so more exercise should mean a lower weight. Of course, this is a very vague statement, and we need to take a lot of things, or a lot of other things into consideration, but this is kind of like what I want to vehiculate here. I hope that you get my point. If on the other hand, the covariance is positive, then it means that the 2 random variables evolve in the same direction. That could be, for instance, the amount of the amount of work that you put into your studies, the amount of hours you put into your studies, and your GPA. In general, the more you work, the better your grades, the higher your grades. The covariance formula is linear, like the expectation. It means that if you multiply one of the random variables by a constant a, which means everything inside x will be multiplied by a, then it is the same thing as putting the a at the front and computing the covariance between x and y alone. Then, forget about this, I need to correct that. Now, the covariance of x plus z between x plus z and y, by linearity again, can be expanded, can be broken up into 2 separate covariants. It will be the covariance between x and y, plus the covariance between z and y. So, this might look a bit complicated. You can break it up into 2 separate covariances. Forget about this again. I think that's some copy pasting here that I failed to erase. Now, if you multiply x by a constant a and y by a constant b, then when you do this expansion, the one I just did above, you can take the constants out of the covariance. So here I am mixing the first property and the second property, so that when I look at the covariance between x and y, a can go out, b can go out as well, and I end up with a times b times the covariance between x and y, plus here I have the covariance between z and by. Again, I can put the b out of the covariance and I get b times the covariance between z and y. The last property is also using the variance formula. It is looking at the variance of the sum of two random variables. Remember that the variance has a square in it, and when you expand the square, you always have the square of the first term, the square of the second term, and there is always a 2 times something something in the middle. Well, when you transpose this to probabilities, you end up with variance of x, first square, plus the variance of y, the first square, plus 2 times the covariance of x and y. Indeed, if we had n different variables paired with x, so we had x plus z plus u plus v plus t and so on, you could break everything up into n separate covariances. True. They'll be very long and tedious to compute, but it would not be difficult. It would just be complicated, a lot of formulas, but not difficult per se. Again, this might not make a lot of sense right now. That might seem very complicated. Once you get used to manipulating those properties, you will see that it's actually not very complicated. You just need to know them. The last one I want to talk about is actually a kind of trivial one, is the covariance between x and itself is equal to the variance of x. And you can check the covariance formula where you put x in both places. Let's take a look. Here, if you have x minus expectation of x, and here you replace y and y by x, you get x minus expectation of x again. Then this means that you get x minus expectation of x squared. And you go back to the variance formula. So the variance of x in some way is a measure of the covariance between x and itself. It's kind of a trivial thing. It doesn't really make sense to say it this way, but that might be very helpful. Now, last week in the when I talked about the variance, I mentioned that the unit of the variance is equal to the square of the unit of x, because there's a square in the formula. And when you say the average age is 28 years old, okay, that's good. But if you say the variance of age then is equal to 5 years squared, what does that mean? And that's why we took the standard deviation. We took the square root to take the square down, pretty much. Here, when you talk about covariance, you are multiplying the units of x by the units of y. And if I look at for instance, the amount of work you put before an exam, which could be measured in hours, and you multiply it by your score, which is a percentage, then how do you interpret the result? It's kind of difficult it's kind of complicated to interpret. The only thing you can tell is, well, if the covariance is positive, when one is high, the other one tends to be high. Or when one is low, the other one tends to be low. They are always going in the same direction. If the covariance is negative, it is opposite directions. To deal with this scale problem, we can use a unit-free measure, and this is what we call the correlation between x and y. The correlation between x and y, which is denoted cor with CO two R's, or we also use this Greek R, which is called rho, R-H-O. This is not a P, this is a rho, is defined as the ratio between the covariance between x and y and the product of the standard deviations. Because look, there is a square root here. Now remember that the covariance of x and y is expressed in terms of unit of x times unit of y. Here, when you have the square root on the variance of x, you would get the unit of x, and here you would get the unit of y. So you would divide the unit of x by the unit of x and the unit of y by the unit of y. Yes, thank you. Here, sorry about this, there's a typo. I will correct that later during the break. So this division here is made to get rid of this weird unit. And as a consequence, we also get that the correlation between x and y is always between -1 and 1. That is also an interesting feature. -1 means extreme negative correlation, linear correlation. 1 means extreme positive correlation. 0 means no correlation at all. One moves and the other one moves, but the way they move does not influence each other. When the correlation is 0, we say that x and y are uncorrelated, or they are linearly uncorrelated. Note, by the way, that from this formula, if the covariance is 0, then the correlation is also 0. So one will also imply the other. Remember that the correlation is just a way to change the unit of the covariance. So it kind of carries out the same interpretation, except that it has a different scale and a different unit. Any questions? Okay, so the bottom line of this section is that we have two other measures which are commonly used to look at the correlation, the covariance, the covariation between two random variables. But as you saw in the properties, you can also do this with more than two random variables. In economics, we are particularly interested in making a distinction between correlation and causation. Correlation does not imply causation. I'm sure you've heard this somewhere. Everybody says it. Two variables could be correlated, but it doesn't mean that one causes the other. And this is the difficulty in economics. Everything happens at the same time. Inflation, unemployment, all those things are just happening at the same time or measured at the same time. And sometimes it is difficult to understand if it starts with a chicken or if it starts with the egg. Does unemployment lead to inflation, or does inflation lead to unemployment? And so on and so forth. And we might observe correlation just by computing this measure using some data, but finding causation is a harder challenge, and this is what we're going to see in the rest of the semester. For the time being, let's move on to conditional probabilities. Conditional probabilities are a concept that you are familiar with without knowing it. So it might seem complicated, you might hear a lot of jargon, but you should be able to, if you think about cases in real life, you should be able to relate. If you look for the slides, there should be on Canvas, there should be a set of slides called 2 random variables. Is it not the case? I thought I put them 2 days ago. Let me take a look. Ah, you got it? Okay, good. Good. Okay. So, going back to conditional probabilities. The formal definition is as follows. The conditional probability of a random variable y given, note that given is highlighted, given the value of a random variable x, which we denote the probability of y being equal to a certain number, given that x is already equal to a certain number, or we also write it p of y given x, is the probability of y taking a value small y, that's one possible realization, when or given that the value of x is fixed at some value small x. It might seem very abstract. I'm going to give you a very simple example. Imagine that the world is composed of circles and non-circles. We also have smokers and non-smokers. And here are a couple of stats I'm going to give you. We know, for instance, that 20% of the people are circles and 80% of the people are not circles. Now, what we know is that among circles, 30% are smokers, and among non-circles, 60% are smokers. Imagine that x is the circle status, 1 if somebody is a circle, and 0 if somebody is not a circle, and y is going to be the smoking status, 1 if somebody is a smoker, 0 if somebody is not a smoker. This piece of information is telling us the following. It tells us that the probability that y is a smoker, so the probability that the next person I meet is a smoker, given that I am looking at circles, is 30%. And the probability that the next person I'm looking at is a non-smoker, given that it is a circle, will be 70%. The word given here, this vertical bar, means that I am already looking at circles. I am looking into circles. Among the circles, in the group of circles, we know that 30% are smokers. So if among circles 30% are smokers, then the number of non-smokers will be 70%. And this here is the complement probability. Inside the world of circles, when I only look at circles, we have smokers and non-smokers. Moreover, we also know that among non-circles, so when I look at only non-circles and I ignore circles, 60% will be smokers. So the probability of y equal to smoker when X is a non-circle, so when I am looking at a non-circle, will be, oops, it shouldn't be 30% here, my bad. It should be 60% here, and here it should be 40%. My bad, I will correct this later. So when I say given, among, or other terms like this, I am restricting myself to a subpopulation of people. Instead of circles and non-circles, you can think about men and women. Given that the next person I meet is a woman, there is a 30% chance it's a smoker. But given that I am looking at a man, there is maybe a 50% chance it's a smoker. The probabilities of finding a smoker will be different whether I know if it's a girl or a boy in the first place. And this is what this conditional says. It assumes that we are looking at that particular portion of the population. The other information we have is that there is a 20% chance of finding a circle in the street and an 80% chance of finding a non-circle. This is the first piece of stats the first numbers I gave you. Note that this first sentence doesn't say anything about smokers. We know that 20% of people are circles and 80% are not. So we just have probability of finding a circle and probability of finding a non-circle. In words, again, we know the probability of meeting a circle or not, 20 versus 80%, and we know the probability of meeting a smoker among circles and non-circles. But there is a thing we don't know. We actually don't know the probability of finding a smoker regardless of whether it's a circle or not. This is not mentioned anywhere. It only says if I know that the next person I meet is a circle, or if I know it's a girl, then I know there is a 30% chance it's a smoker. If I know the next person I meet is a man, then I know it's another probability of being a smoker. But if I don't know who I'm going to meet, I don't know if this is a circle or not, then I have no way to know the probability of that person, circle or not, being a smoker. So here is what we don't know now. We don't know the probability of a smoker and a non-smoker. We don't know if I meet a smoker. We don't know the chance that this is a man or woman, or this is a circle or non-circle. What we know is, once I look at circles, I know the probability of looking at smokers. But once I look at a smoker, I don't know the probability of finding a circle. It is going to be very confusing. You're going to need to read this over and over and over again until it makes sense, really. I know it's going to be a pain. Unfortunately, this is a necessary evil. This is one of those things that we need to understand because it's actually one of the statistics, one of those numbers that you can find on TV or in newspapers which are wrongly formulated. And this is also sometimes a reason why some politicians disagree with one another. They might pull up a statistic that they found in a survey or in a survey or anywhere, but they might not be able to say it correctly, and because of that, there is a disagreement about what the statistic means, and sometimes some politicians do know that this is not the right way to say it, but they choose willingly to say it in the wrong way to influence the population. It is not an easy concept to grasp, but once you know it, it will make a lot of things clearer, and you will see that you can find a lot of BS out there when it comes to people reporting some numbers and some statistics. So, in words, what we don't know is, we don't know the probability of meeting a smoker because we don't know how many there are in the whole population. We only know how many there are among circles and among non-circles. And we don't know the probability of meeting a circle among smokers or non-smokers. So we know one conditional probability, but we don't know it the other way around. A typical challenge is actually to try to go from one to the other. That requires the use of other formulas, which I do not want to talk about in this course, but just to give you an idea, this is the kind of things that we are interested in when we look at conditional probabilities in statistics. Now, I need to make something clear about the terms that I'm going to use from now on. First of all, when I talk about the distribution of x or y alone, the probability that x is equal to 1, the probability that y is equal to 2, this is what we call the marginal distribution. For instance, the probability that y is equal to smoker. That's totally marginal, there is no x in it. Then, there is what we call the joint distribution. This is what we saw in the previous lecture. This is the distribution of the intersection of x and y. For instance, the probability of meeting somebody who is a smoker and a circle at the same time. So when you think joint, you should think the intersection sign, or you should think the comma inside the probability. And the last one I just mentioned is the conditional probability. Every time you think about conditional, you should think about a vertical bar. What's after the vertical bar is the condition. The condition is, I already know that I am looking at a non-circle. Then, given that, knowing that, what is the probability that this non-circle that I'm looking at is a smoker? And note that x given y is not the same as y given x. If it's not clear to you right now, just admit it. It is not the same. And try to figure out why. Ask me, ask the TAs. And just so you know, it is not the same. You cannot prove me wrong. It's just how it is. It is not the same. So if you don't understand why right away, just tell yourself they are not. I cannot take any shortcuts if there is an exercise in the midterm. They are not the same. And then you're going to have to think about it, read it again, maybe listen to this lecture again until you understand the difference. Now, it turns out that conditional probabilities and joint probabilities are related. The probability that x is equal to a certain number and at the same time y is equal to a certain number is the probability that x is equal to x, that's a marginal probability, times a conditional probability. Note that this formula could also go the other way around. Here, if I have x is equal to x alone, then I have my x after my vertical bar. Why? Because here I am looking already at x is equal to that specific small x. And I need to multiply by the probability of that thing happening. I can do it the other way around, but in this case, if I have y last here, after the vertical bar, I need to have y alone here. This is a very important formula. You will not be able to get around it. You'll have to know it. You'll have to know how to use it if you want to get some answers correct in the midterm and the final. Don't worry, we're going to get some practice. Now again, as I mentioned, this is not the same as this. And this probability where y is first, x is second, is not the same as the probability where x is first and y is second. Problem set 1 is based on both of these lectures. This lecture and the one from last week. I just finished recording the tutorial and I am about to upload it on Canvas right after this lecture. It's already on YouTube if you want to take a look at it. I just haven't made the page on Canvas yet. So, because of all these different distinctions, when two random variables are correlated, I cannot look at the distribution of one without looking at the distribution of the others. So, in particular, what we're going to need is contingency tables. Those are tables which are going to contain the joint distribution of two or more variables. 2 is already enough. Do not worry about this. I will not give you a table with 3 random variables. That would be too much of a pain. So, a contingency table contains the probability of x being equal to a certain number and y being equal to a certain number. On the other hand, we can also use probability trees, but probability trees do not contain joint probabilities. Instead, they illustrate conditional probabilities in a graphical way. So you can use these two tools together. I'm going to show you what they look like and how to make them. And you will need to know how to use both of them. So let's consider two random variables. The contingency table here represents the joint probabilities. And so in order to avoid putting this intersection sign and this whole thing the whole time, I'm going to just use a shortcut, a shorthand, and write small x1, comma, y, small y1. This means this is the probability that big X is equal to small x1 and big Y is equal to small y1. And so, by listing all the values that Y can take here in rows and all the values that X can take here in column, in the middle, I'm going to list all of these probabilities. Note that in the case where X is equal to 1, there are 3 cells where this happens. It happens here, here, and here. The idea is that X can be equal to x1 when y is equal to y1, or when y is equal to y2, or when y is equal to y3. Same, x can be equal to 2 when y is equal to y1, or y2, or y3. So it turns out that when you add all the numbers where x1 is going to show up, that will give you the overall probability that x is equal to x1. There is the case where x is x1 and y is y1, y is y2, and y is y3. But in all of these cases, x is equal to x1. So these are joint probabilities, and by adding them up, I obtain the marginal probability. And this is why this p of x here shows up under the y's. And at the same time, on the other hand, p of y shows up next to these two x's. Here, y1 shows up in 2 places, here and here. You add them up and you get the marginal probability of y being equal to y1. Now, since x can be equal to either x1 or x2, when you add these two probabilities together, you get 100%. There is a 100% chance that x is equal to x2 or x1. The same way, when you add the three different probabilities for y, because y can be equal to three different values, when you add them all, you should get to 100%. So this 100% is always there. And it will always be the sum of all the guys here and of all the guys here. Another great way to check that your computations are correct. And I can do the same for the marginal distribution of y. It is one of these things that might seem very cryptic at the beginning, and after manipulating them, it will make sense. So it's one of these things where it's really a learning by doing process. You need to do it several times. Maybe at the beginning you have to apply formulas that you do not necessarily understand, and eventually something is going to click, if it has not clicked already. I'm talking with my experience here. It took me a lot of time to understand how to perfectly manipulate these things. I did not get it right away. I learned the formulas by heart. I got good grades, but it took me one more semester to finally understand the relationships between all of these different marginal, conditional, and joint probabilities. Now, probability trees are going to look like this here. We start on the left and we go to the right. X, first of all, can take two values. We saw that it can be equal to x1 or to x2. Now, after that, here we have y that can either be equal to y1, y2, or y3. So, the numbers you get at the end of each branch will be conditional probabilities. Here, for instance, the first one, this is the probability of y being equal to y1 given, because we are already here, we are already in the case where x is equal to x1. So given that x is equal to x1. The second branch is going to have the same condition because it comes from the same node here. The third branch is going to have the same condition as well because it also comes from the same branch. In the second part of the tree, the condition at the end will be x is equal to x2 because now we are on the second branch. So this says, for instance, first I meet a person and it's a circle or a non-circle. Remember, we use the numbers 20% and 80% for that particular example. And then among circle, you meet a circle first, and then that circle could be a smoker, non-smoker, or I don't know, there's a third option. You can think of a social smoker, someone who's not a regular smoker, but who smokes every now and then. The probabilities will not be declining as you move from left to right. This is 20% and 80%, but this might be 30%, 30%, and 40%. It's not that they decline, because here we are looking inside the circles. Inside the circles, there could be 90% of smokers. For instance, among French people, there is 67 million people, 67 million people which are French. Well, at the scale of the world, that's very small. That's 1% or something? No, lower, 0.1% or something. But among French people, the probability of finding a smoker is going to be something like 30%. I don't know, maybe 20%. And you can see that the probability is not necessarily smaller. So, the contingency table shows joint probabilities. So if you want to compute conditional probabilities from here, you have to use the formula I showed you before. That was this formula. If you know this, the left-hand side, and you know this because it's also in the table, then you can take this on the left-hand side to find that. And this is what I showed you in the first tutorial, actually. Now, if instead this is what I give you conditional probabilities, then you can use the formula directly. You know this, you might know that, especially when x is first, and so you can find this easily. This will be the smaller probability, Seamus, to answer your question. The intersection is a multiplication of two probabilities. And because both probabilities are between 0 and 1, when you multiply 0 point something by 0 point something, then the number you get will be even smaller. So the intersection will be the smallest probability of the three, if that can help. Now, I'm pretty sure your brain is already hammered, so let's take a break here. Let's take a 15 minutes break and resume at 6:40, and I will show you an example. This example is gonna cover the whole lecture. It's gonna cover covariance, correlation, conditional stuff. So hopefully that will give you an idea of how to manipulate the formulas and how to distinguish between all these terms. See you at 6:40. Yes, sorry. Absolutely, my bad. 9:40. Yeah. I'm in France right now. It's 6:40 here. Sorry, 9:40. Yes.
So it's not just a
All right. Let's get back in. Wait a minute. Let me adjust one thing first. Yeah. There we go. Okay. So, where were we? I just talked about conditional probabilities, which are probabilities when we restrict ourselves to looking at a specific subgroup of the population. I talked about marginal probabilities, which is the case where I just talk about X or Y alone without including them both. And then I talked about joint probabilities, which are the probabilities of X and Y realizing themselves at the same time. I give you a bunch of fancy formulas. This is how it looks in an example. Honestly, I think it's going to be easier once you get to put some numbers on them. So, let's start with the random variable x that can be equal to 1 or 2. Let's assume that there is a random variable y that can be equal to 1, 2, or 3. And the first contingency table I'm giving you here contains these 6 numbers. So I haven't given you, technically, the marginal probabilities yet. I just give you the joint probabilities, and from there you can guess what the marginal probabilities will be. So first of all, let's look at the probability that x is equal to 1. It will be the sum of all the probabilities where x is equal to 1 shows up, which is this cell, and this cell. Note that this sum represents or. I talked about this, it's called the union. X is equal to 1 and y is equal to 1, or x can be 1 and y can be 2, or x can be 1 and y can be 3. When you add them up, you are adding up all the probabilities where x is equal to 1 shows up, and that gives you a result of 0.6. Here. The same way we can do the probability that x is equal to 2. We add the probability that x is equal to 2 and y is equal to 1, x is equal to 2 and y is equal to 2, and x is equal to 2 and y is equal to 3. 0.1 plus 0.2 plus 0.1, 0.4. Note again that this 0.6 and this 0.4, when you add them up, they sum up to 1 or 100%. If they don't, either you made a mistake or I made a mistake in the numbers I used in the table. It's one or the other. If you are sure of yourself in the midterm and the final, and you think you're correct, yet those two numbers do not match, then you can call me and say, hey, I think this is supposed to sum up to 1 and it doesn't, so maybe I made a mistake. That has happened before, so it's possible. So in this case, the probabilities I gave you are these 6. I gave you the joint probabilities. You can get the marginal probabilities using these joint probabilities. And now that we have the joint and the marginal, we can find the conditional. But remember, to use this formula, which is long and complicated, we need 2 probabilities out of 3. Either the joint and the marginal, or the joint and the conditional, or the conditional and the marginal. Here, I started with the joint. You could guess the marginal. And now that you have these 2, we will be able to compute the conditional probabilities. In an exam, I could also leave a couple of blanks here and there, and you have to guess what these numbers in the blanks are depending on the other numbers. For instance, if I leave this one blank, but I give you the 0.6, you can guess, you can find that here it must be equal to 0.1. Here, if it's 0.6, and you don't have this one, and you don't have this one, then you know that if this is 0.6, this has to be 0.4. And once you know that this is 0.4, you will know that this has to be 0.1. So play around with those things. Make sure you know how how to compute probabilities using the ones you're given. Okay, now once the table is complete, we are going to get into the serious stuff. First, let's go from the joint probabilities to the conditional probabilities. I have the joint, I have the marginal, so if I want to compute the probability of y equal to 1 given x is equal to 1, remember at the top I put a comma, this is the joint, always, and at the bottom I put the same probability as the one that shows up inside the condition. Because remember, if I put the condition, it means I am already looking at this subgroup. So I need to take into account the probability of finding this subgroup. These two numbers are from the table, and you get 50%. So the interpretation in words is that when x is equal to 1, or given that x is equal to 1, there is a 50% chance that y is also equal to 1. The same way, we can find the probability that y is equal to 2 given x is equal to 1, and the probability that y is equal to 3 given x is equal to 1. I strongly suggest you to find these two numbers using the formulas above. That's a great practice to make sure you understand what's going on. Here are 3 more probabilities that correspond this time to the case where x is equal to 2. So it's like going through the second branch of the tree. Note that when x is equal to 1, so here, here, and here, y can either be 1, 2, or 3. And if I add 0.1667, 0.3333, and 0.5, I get 1. In words, once I am looking at the circle, I will find either smokers or non-smokers. If I add all the smokers and all the non-smokers among the circles, I will get back to 100% of my circles. It's another way to check your computations. Okay. One thing I mentioned in the previous lecture about events will also be true for random variables. I mentioned that variables can be correlated. We can also say that they can be independent, but careful, if they are not correlated, it doesn't mean they are independent. It's kind of a tricky thing. Those are two separate terms. Two random variables are independent if the realization of one does not affect the probability of the other. So, they are independent if the conditional probability is equal to the marginal probability, and the condition is not even needed. And in this case, if you go back to your previous formula, when you want to compute the joint probability, you don't even need to compute conditional probability anymore. You don't need to get the condition here. You just take the product of two marginal probabilities. An example. Imagine that the number of smokers, the proportion of smokers among men and women is the same. 30% of men smoke, but also 30% of women smoke. It means that it doesn't matter if I look at a man or a woman, the probability of finding a smoker will be the same. It will be 30%. I don't need to think, given that I am already looking at a man or a woman, then the probability is different. No. If the probability is the same across genders, then the gender doesn't matter and smoking status and gender would be independent of each other. A consequence of this definition, and I don't want to show the math, it's not very complicated, but no need to show the math, is that when two random variables are independent, their covariance is equal to 0. The idea is that they do not move together. They do whatever they want, but they do not depend on each other. So they do not move in any sort of coordinated or non-coordinated way. This also means that if the covariance is 0, the correlation will be 0. So when variables are independent, then it means their correlation is equal to 0 and their covariance is equal to 0. But the reverse is not true. So if you find a covariance of 0, it just means the variables are not correlated in a linear sense. And that's a kind of tricky point here. But the idea is that the formula of correlation and covariance measures the extent to which variables are proportional to each other. They measure linear correlation. But some variables could be non-linearly correlated. In this case, their covariance is 0. Their correlation will be 0 because the formulas would not capture this linear correlation. However, they would not be independent. This thing would not be true. It's just that they are not correlated in a linear way. And this is something I will come back to later on once we talk about regressions. So that will be either in 2 weeks or 3 weeks. Now, because we talked about conditional probabilities, we need to talk about conditional moments. Conditional expectation, conditional variance. All those things are going to exist as well. And I'm going to start with an example which is going to be different from circles and smokers. Imagine that Y is the temperature in Celsius degrees, and X is a location that is either Vancouver or Asparin. This is where I am right now. You can type it on Google Maps. This is where I'm from. So X could be 1 if it's Vancouver and 0 if it's Asparin. It doesn't really matter. Now, I found these numbers somewhere on Google, I think, and I found that the average temperature in a year in Asparin is 13.5 degrees and in Vancouver is around 11 degrees. It's particularly hot in the summer. It's a bit hotter than Vancouver, maybe 4 more degrees on average. And it's around the same cold in the winter. Note that the average temperature will not be the same if I am looking at Asparin or Paris or Vancouver or Montreal or Toronto. So the average is not the same everywhere. So in this sense, the average is also kind of random. So the conditional expectation has the following definition. Think about two random variables x and y. The expectation of y conditional on x, which is written as expectation of y given that x is equal to small x, will be the sum of the different values that y will take times their probabilities. But note that because I have a condition here, I need to have a condition there. That has to match. So imagine, for instance, that I have n days or 365 days in a year, and I look at the temperature at noon every day for 1 year. Then I can compute the average temperature given that I am in Asparin by looking at all the times that all the different values, all the different temperatures we had, times their probability, times the frequency at which they happened during the year. But because I say given we are in Asparin, then I will be only looking at the temperature from Asparin. And you could do the same in Vancouver. But again, I mentioned that the expectation is different whether I look at one city or another. And so, for this reason, a conditional expectation is random because it depends on the value of x, and x is a random variable. Again, that might be hard to wrap your head around at the beginning. Take it for granted, and eventually, after manipulating a couple times, after reading about it, this concept is going to sink in. The concept of a conditional expectation is crucial for this course. I'm pretty sure I will ask you something about this in literally every assignment, the midterm and the final. Honestly, from what I can think of right now, this will show up everywhere. And probably in every single problem set as well. It is not very different from the formula for the expectation that I gave in the previous lecture. It's just that this time, the probability here has to contain this condition. So now it's a conditional probability, not a marginal probability anymore. That's all. So you just have to find the right probability to use. That's it. Now imagine that my hometown and Vancouver were the only two locations in the world. Then if I want to compute the world average temperature, I just have to take the average of the temperature in Asparin and the temperature in Vancouver. So I take the average of, 13.5 and 11 degrees. So the final expectation, sorry, that's not next, that should be a y. The final expectation is an actual average of the conditional expectations. I took the average, I took the expectation of these two expectations. So I took an expectation of expectations. And this is actually a theorem. The final expectation that doesn't have any condition, you can see here, y is alone, is the expectation of the conditional expectations. So I will take a second average of my averages over the different values of x. This is one conditional expectation. This is one conditional expectation. Now, there might be different probabilities of being in each city, because my town is very small, 8,000 people, and Vancouver is pretty small, 800,000. Oh, it's actually 100 times bigger, now that I think about it. Okay. So, if I want to compute the average temperature in the world, then I would do the probability of being in Asparin times the average temperature of Asparin, plus the probability of being in Vancouver times the average temperature of Vancouver. So I would take an average of averages. And this is what we call the law of iterated expectations. We iterate, we take an expectation on an expectation. And if I had a third variable to condition on, I had another z, given x and given z, then I will have to take expectation of expectation of expectations. Not very difficult, super annoying to compute. You will have a long stretch of computations to perform, but it's just an application of a formula. The conditional variance is going to be the same as the regular variance, except that now we need the conditional probability here and the expectation, which is inside the square, remember, is now the conditional expectation. So here we have added two conditions. We have conditional on x here inside the expectation, and here we have the whole thing conditional on x. So the probability to put there is a conditional probability, and here we use a conditional expectation. The second formula, the one I use most of the time, but both should be known, is going to be the same except that we have conditional expectations. So here first I compute my conditional expectation and then I take the square of it. Here I compute the conditional expectation of y squared. Once you know how to compute these things, and we are going to go through it in the example right now, it's just about practicing more and more, but there is nothing difficult per se in it. You just have to practice a lot. So, let's go back to our previous exercise, but now we are going to compute all the things we have covered so far. First of all, we are going to compute the expectations without any conditions and variances as well. This is coming from the first lecture, so it shouldn't be too complicated. Then we can compute the covariance and the correlation. Again, no conditional stuff here. The conditional stuff starts here with the conditional expectations and the conditional variances. In order to compute these conditional expectations and variances, I am going to need the conditional probabilities. So I'm going to have to perform a couple of computations to get all of my conditional probabilities. But first of all, let's compute the regular expectations. If you want, I can give you a minute or two if you want to grab a piece of paper and try to do it on your own. I suggest you have the table, this table, on the side, because I'm going to be moving through and they will not show up on the slides anymore. But I will use these numbers all the time. First, the expectation of x. There is no condition here, so we just have to use the marginal probabilities, the ones here at the bottom and here on the far right. X can be equal to either 1 or 2, so it's going to be 1 times the probability of being equal to 1 plus 2 times the probability of being equal to 2. Here is going to be 1 times 0.6 plus 2 times 0.4, and that gives you 1.4. The expectation of y can be obtained equivalently by multiplying each value y can take by the corresponding probability. 1 times the probability of y being equal to 1, plus 2 times the probability of y being equal to 2, plus 3 times the probability of y being equal to 3. And you get 1.9. The variance should not be too complicated either. But first, since I want to use the second formula, I'm going to need the expectation of x squared and the expectation of y squared. The expectation of x squared is the same as before, except that the values that x can take are squared up. So 1 squared times the probability that x is equal to 1 plus 2 squared times the probability that x is equal to 2. Sorry about this 0.6, that's this number. I will take it away. And that is equal to 1 times 0.6 plus 2 squared times 0.4. And that gives you the number 2.2. Again, forget about this guy, delete it. The expectation of y squared equivalently will be 1 times 0.4 plus 2 squared times 0.3 plus 3 squared times 0.3. Same as here, but I take 1 squared, 2 squared, and 3 squared. And that gives me 4.3. Now, I am ready to compute the variance. The variance is going to be this 2.2 minus the expectation of x I found here, 1.4 squared. 2.2 minus 1.4 squared will be equal to 0.24. Same for the variance of y. It's going to be equal to 4.3 minus 1.9 squared. And that will give you 0.69. If you want to compute the standard deviation, take the square root of these two numbers and you're done. Let me know if you are okay with it so far and if you want me to slow down. I will wait a bit. I'll wait a minute or two before I move on to covariance and correlation. Here, you should not put any small x because small x is 1 and 2. And small y will be 1, 2, and 3. So every time I put big X here, I mean the random variable is equal to 1. If you put a small x here, this is wrong because small x is not a random variable. Small x is one particular value. So when you say the probability that small x is equal to 1 means, well, is x equal to 1? In which case, this probability is equal to 100%, or is it equal to 0, or is it not equal to 1, in which case the probability will be 0. So be careful. These are the small x's, the 1 and the 2. Here, the small y's are the 1, the 2, and the 3. So make sure you do not make mistakes when you use the notation. That will make a difference in exams. I totally agree with you. Not hard, just takes time, and eventually you'll do it fast. But the first times, you need to make sure you use the right numbers from the right columns, from the right cells, and it's a painful process. But remember when you learn derivatives. I'm pretty sure that the first time you learned derivatives and you had to learn this whole table of formulas with the product rule, the 1 over x rule, the log, the square root rule, the log, and so on, and the exponential. I'm pretty sure finding derivatives was kind of painful. But I'm pretty sure right now that I could ask you to compute a marginal rate of substitution and you would do it in less than 5 minutes. You would take two derivatives, then take the ratio, and you would get it done very fast. So it's all about practice. Okay. Also, I suggest you use the original formula for extra practice and to double check your results. I will refer you to problem set 1, where I compute a variance in two different ways with both formulas to give you a template so that you can find the result using two different formulas. I really strongly suggest you do it at home. I have received actually complaint in the past that sometimes I was not giving enough examples, but remember that you have examples in the lecture notes, you have examples in the problem sets, you will go through examples in assignments, and you're always free to look at any book, try an exercise, and then ask me to look at your work. That's what I'm paid for. So if you want to do extra practice and ask me about it, I can take a look at your computations, and I'll tell you if they are correct or not. Okay, now let's get into the covariance. The covariance is probably the most painful one to compute. It's just long, it's just a grind. To compute the covariance, we need the joint probabilities because we're talking about x and y moving at the same time. Note here that we have 1, 2, 3, 4, 5, and 6 different probabilities. These probabilities correspond to all the joint probabilities that you find in the contingency table. So, a way to make sure you are using the correct numbers when you compute the covariance is you have to use all the joint probabilities, all of them. All of them have to show up eventually. So it means that we should see 0.1 3 times, we should see 0.2 twice, and we should see 0.3 once. 0.3 once, 0.1, 0.1, 0.1, and 0.2, 0.2. Okay, good. Now, every time we multiply the probabilities by the corresponding values minus their expectation. 1.4 was the expectation of x. 1.9 is the expectation of y. So this probability, 0.3, corresponds to the probability that x is equal to 1 and y is equal to 1 as well. So, in my formula, I will have 0.3 times, here 1 for x minus 1.4, and 1 for y minus 1.1. Then this 0.1 corresponds to the case where x is equal to 2 and where y is equal to 1. So 2 minus 1.4, 1 minus 1.9. Note that there is a lot of copy pasting here. And once you do this in your assignments with R, I expect you to show me the whole formula. For assignment 1 as well, I want you to show me everything step by step detailed. I do not want you to use a magic formula from R. I want you to pretty much use R as a calculator. But there's a lot of copy pasting. And if you do all of these computations, you get 0.04. In fact, this covariance is pretty small. It is not exactly 0, but it's pretty small. Now, if you want to get a correlation, well, everything is ready. We have the covariance, we put it on the top. We have the variances, we put them at the bottom, but remember, we take the square root of them. So we actually look at the standard deviations. So the correlation should be the last computation because it uses a bunch of things you've done before. The correlation uses covariance and variances. For the covariance and the variances, you need the expectations. So you start with the expectations. Expectation first, then move on to the variance, then move on to the covariance, and then finally move on to the correlation. I will not ask you to compute the correlation first in an exercise unless there is an easier and faster way to do it than using the grinding formulas. Okay, let's move on to the conditional stuff. Oh, sorry. You can also use the second formula for the covariance, expectation of x times y minus expectation of x times expectation of y, and you should find the same result. Feel free to do it at home. Send me a picture by email, let me know, and I will take a look. If you find the same result, well, then you're correct. Otherwise, I can help you find where your errors are. The conditional stuff now. To compute conditional expectations, conditional variances, and so on, we need the conditional probabilities. And we don't have them yet. We only have the joint probabilities and the marginal probabilities. So let's just grind them. I'm going to compute all the possible probabilities, and I'm going to use the formula every time. So the probability of y being 1 given that x is being 1, then is going to be probability that x is equal to 1 and y is equal to 1 divided by what's in the condition. So here it's x is equal to 1, and you will see here at the bottom x is equal to 1, x is equal to 1, x is equal to 1. Here the condition becomes x is equal to 2, and here you have x is equal to 2, x is equal to 2, x is equal to 2. These numbers were found before talking about conditional moments, but I rewrote them just to give you the full formulas. Now I can actually place them in the tree. Here on this first branch we have x is equal to 1, and given that x is equal to 1, we have y1 is equal to 1, 2, and 3. Here actually you can put x1 is equal to 1 and x2 is equal to 2. It is now time for conditional expectations. The first one we want is the expectation of y given that x is equal to 1. So we need to find all the conditional probabilities where the condition is that x is equal to 1. So we need this one, and this one. In the first case, y will be equal to 1 times the probability of being equal to 1 when x is equal to 1, so that's 8.5. Then when it's equal to 2, it's going to be 2 times 0.1667. And finally, for the third one, it will be 3 times the probability that is equal to 3, which is 0.3333. And the conditional expectation is equal to 1.8333. Okay? I'll take a minute here, give you some time to let that whole thing sink in. I want to point out that when you fix a condition here, the condition shows up everywhere, every time. It's there every time. And this is a very important aspect. It's a way to make sure that you're using the correct formulas, the correct numbers. When it comes to probabilities and learning all these rules and formulae, I use many mnemonic devices, many ways to remember why, when you put x equal to 1 in the condition, and so on and so forth. It is very easy to mix things up, so I strongly suggest you to find a way to remember these things in one way or another. To each their own. You will need to memorize most of the formulae. I will print a cheat sheet for you guys containing some formulae for the midterm. I will show you in advance what formulae I will give you, and whatever formulae I do not give you, you will have to know. And potentially, I could ask you about anything. So probably the formulae will be, the cheat sheet will be 1 page long with a bunch of formulae, and then there's a couple more that you might need to use and that you will have to remember. So I will give you probably the most annoying ones to remember, and I will give you the most annoying ones in the cheat sheet, and I will let the most important ones for you to memorize by heart. There are some formulas that I think you guys and myself, anybody in economics, should know by heart. Now, I also used the law of iterated expectations to double check my result. Now that I have the conditional expectations, I can actually take their expectation. So here, when I have the expectation of y given x is equal to 1, I can multiply it by the probability that x is equal to 1. That's what's inside my condition, and here as well. These are the numbers, and that gives you again 1.9, which is roughly the expectation of y that we got 2 slides ago. This second part is actually the expectation of y given x is equal to 2. So now I need to include all the probabilities that contain the condition x is equal to 2. And that's how I got this number 2. And this number 2 is the one used here. I should just swap these two bullet points, I guess. Okay, I have one more slide and then we'll go to another break. I have one conditional variance that I am detailing here, and the other one I wrote its number, its answer right away, and I will let you find it out by yourself. Let's first use the first formula. So the first formula looks at the probability times the square of the value of y minus the conditional expectation. Not very different from a regular variance formula. So here, we always have the condition x is equal to 1. It's everywhere. The probability that y is equal to 1 when x is equal to 1 is 0.5, and so on. And then you multiply this by the squared deviation from the conditional expectation. Here y is equal to 1, and this is why we have this 1, minus the conditional expectation. Here this 2 is going to match this 2, minus the conditional expectation. And here this 3 will match this 3 minus the conditional expectation. The hardest part is to write it down. It's long and complicated, but then you can use a calculator. Calculators will be allowed in the exam, don't worry about this. If they are not needed, then the computations will be easy enough, but you can consider that it's going to be allowed. Let's use the second formula and hopefully get the same result. So let's compute the conditional expectation of y squared conditional on x is equal to 1. Note that this one, we already found it 2 slides ago. So this second part is pretty much done. We just need to square it up. This is what we have left to do. So I look at all the conditional probabilities where this condition appears, and every time I multiply my y by itself. So I take the square. So 1 squared, 2 squared, 3 squared. The condition inside is always the same. And I get this number for the first term in the variance. The second term of the variance is here. It is 1.833, there's another 3 I think, squared. And finally, you take the difference, and that gives you 0.8055, which, rounded off, goes back to, well, it's actually exactly the same result. Both results are rounded off though. 2 ways to get the same result. I have to say that in general, the second formula is generally easier to use, and that's why I tend to use the second formula. The conditional variance when x is equal to 2 is equal to 0.5. And I will let you do it on your own. So, a summary of this big lecture. When we have 2 or more random variables, things get complicated very quickly. Formulae get way longer. You need to make sure you know the difference between the joint distribution, the marginal distribution, and the conditional distribution. Make sure you know how to link them, so make sure you know the formula between the three. Know how to complete a contingency table, as well as make a probability tree. I might ask you in the exam, I might give you some conditional probabilities, and I might ask you to make the whole contingency tree. The whole probability tree. Covariance and correlation are the new measures added to the pool of measures to know about random variables. And one last thing about independence, it will make more sense next week and in particular 2 weeks from now. Independence implies that covariance and correlation are equal to 0, but the reverse is not true unless the random variables are normally distributed. But this, we will talk about it in the next lecture. In the meantime, have a good rest of your week and see you in the next one. Bye.